we went back to the essential or fundamental physical variables or physical quantities that represent the physics of acoustics. Pressure, density, velocity are three fundamental representative physical variables. And intensity is also one of very important physical measures that certainly expresses the power per unit area. What I mean power is acoustic power that transmitting certain plane that has unit area. Okay, and we found that the active intensity or average intensity in complex form is 1/2 the real part of magnitude, complex magnitude of pressure multiplied by the conjugate of complex magnitude of velocity. And the reactive part on the other hand is 1/2 imaginary part of. Okay. That is only valid when we use the complex notation to express pressure and velocity. Okay, that is the result. Okay, now let's go back to the analysis problem of acoustics again. Okay. For example, for a string problem, the basic approach was, one is using Green's function, and second one is using eigenfunctions. Okay. The same things can be applied for acoustics problem. Okay, in general. However, there is one other approach that is possible to be applied to 3D acoustics problem. That is what we call Kirchhoff-Helmholtz integral equation. I always make a mistake to write down his name, Kirchhoff. What is it? Kirchhoff? Huh? I don't know. Kirchhoff-Helmholtz integral equation. As the name indicates, this is integral equation. Therefore, the approach is quite different compared with what we learned before. Okay, let's start with the one-dimensional case. That means to start with the simplest case. suppose I have a pressure that depends only on x and t. It's a one-dimensional pressure field, like I have duct. And I have coordinate starting over here, that is x. And acoustic wave that is governed by this one-dimensional waveguide. Acoustic wave governing equation can be written as follows. That is inhomogeneous partial differential equation that governs the wave propagation in one-dimensional duct. Okay. This is the external pressure field. Okay. And strangely, we have a minus over here. Okay, that comes from the sign convention, actually. If we think about the string problem, okay, because we do know very well about the wave propagation in string. Whenever we have some questions, maybe we back to the string problem to make sure what's going on over there. So for the string problem, if the tension is constant, taut string case, this is the external force that was seen by the infinitesimal element of dx. Okay, and we have been using the coordinate like this. Okay, and then maybe it's natural to consider the external force acting like that as fxt. Okay, according to the sign convention. Then that has to be balanced by d square y, dt square, and rho l dx. So rho l is the mass per unit length, and the dx is the linearized length that we are considering, right? Okay, then equation of motion using this pictorial equation can be deduced like this. Okay, y component would be what? The y component due to this tension is a t dy dx, and the y component of this t would be t dy dx plus d square y dx square dx due to Taylor expansion, right? Right? Okay. Y component of this is a t dy dx because dy dx is the slope at this point. And the slope at this point is what? Dy dx plus d square y dx square dx. That is simply the Taylor expansion of this slope. So on, right?